Should I start? All right. Hello. My name is Rieksts. I'm a software developer at Health Market Science. And today I'm going to be talking about how we made the transition from a NoSQL relational database to a NoSQL database. So the first thing I wanted to talk about a little bit is what we do at Health Market Science. We manage a lot of practitioner data. So we'll take in many sources and consolidate that down to a view of a practitioner. We use this to work with pharmacies and other healthcare industries to cleanse their data and reduce fraud. So one example of this would be if you go into your local pharmacy, you ask for a prescription, we're going to provide the data to see whether that doctor is able to prescribe or not. Another thing we do is we do reports. So if you have healthcare data and you need to report to the government, we'll help you generate a lot of those reports. And the last thing I wanted to say is we also provide key market insight as far as drug targeting for other healthcare industries. Now the first thing I want to talk about is our business is divided into two segments. The first segment is master data management, the second one being our claims warehouse. Now on both of these segments have the three V's, variety, velocity, and volume. On the master data management side, we have variety and velocity. So we take in over 2,000 sources of data, all with different schemas, and each of these schemas is changing over time. So it may not be the same schema between two different files we receive. We have 6 million unique practitioners that we manage and keep track of for over 10 years. And I'll get a little bit more into that in the next couple slides. On the claim side, we have over 1 billion claims. And this is a huge volume inside of our database. We also keep these claims data for 5 years. So we need to manage something that will hold data for extended time. Now, I want to focus on the master data management side of our business. So many of you may not be familiar with master data management, so I'm just going to give a quick overview of how the data flows through our system. The main idea behind master data management is we have many sources, and we want to provide a consistent view of that data that is precise information about a doctor. So we'll get data in from our customer, may contribute back to our data. We'll get information in from the web. We'll crawl the web, looking at hospital websites. And we'll get data from the government. We take all these sources in, and then we validate and standardize the data. So we'll throw out bad data, and then we'll standardize the data into a standard format. So let's say phone number. Some people have phone number as spaces. Some people have dashes. Some people have nothing in between at all. And we need to bring all those phone numbers into a standard format. We also do it with many other fields as well. After we've standardized the data, we need to match data together. So we're going to say that these two sources are talking about the same practitioner. In some ways, some example is last name. Obviously, this is a very simple example, but we would not actually use, but our matching algorithms are proprietary. After we've determined that two sources are indeed, or two or more sources are talking about the same practitioner, we need to consolidate that into a single view of that practitioner. And I'm going to walk through an example. So if we have a record, John David Smith and Mike Steve Smith, we're going to say these two matched and they are the same practitioner. Now, source A and source B, source B has a good first name. We trust the source B for its first name. So we're going to bring Mike over and call that the consolidated record. But source A, we know the middle name is good, so we're going to bring that middle name over. And then the last name is the same, so it doesn't matter which one we bring over. And this is a consolidated view of our record. In our legacy system, this process took a week. We have a relational database And we use JBoss with JBoss MQ. Now, a lot of the time taken for this was due to the data checks and analytics performed at the back end. To speed this up, we introduced Cassandra into our stack. So we use Cassandra now as our primary system of record. We use DropWizard for our REST services, which I'll talk a little bit about in a few slides. We use Apache as our front end. And for our client deliverables, we use Oracle to extract the data. And then Storm is our real-time processing system, does distributed processing for us. And then we have the custom MDM code that I was just talking about. All right, so I wanted to talk briefly about our data model. When we were going from a relational database to a NoSQL, we switched from thinking about joins to thinking about the entity as a full entity. We build up that record over time. So as these sources come in, they'll build pieces of that record. Then when we fetch the data out of Cassandra, we get the full record. And we found that the primary key determined a lot of how we queried our database. So we definitely want to choose your primary key very carefully. Now, to help ease that pain, we introduced a project called Cassandra Indexing. This is out on GitHub, freely available. What it does is it does a two-phase fetch. In the first phase, you're going to get your primary keys based on the index. And then based on those primary keys, you can do a direct fetch to get your data. So I'm going to walk through an example of flow. So if we have column 1 and column 2 as our key, and we have our index column 2, column 1, you can then fetch from your application to the index, get back your list of keys, and then you can do some filter on those keys if you have composite keys. We do a lot of composites. And then, based on this filtered list of keys, you can get back your data or get back a single record. Now, a little bit more concrete example. We have first name, last name. The index is on last name, first name. So our data is John Smith. We have Steve Smith and David Jones. Now, when you look on the index, you can ask for John Smith, or for Smith, and you'll get back John Smith and Steve Smith, but you will not get back David Jones. And if you ask for Jones, then you get back the single record. And we integrated this into our system here. So we have our tab files which come in, and then our relational database is triggers. So we added a lot of triggers into that relational database when it goes into Cassandra. And then at that point, we extract it into the client deliverable. And then in our real-time system, we started adding Storm into the mix. So then now Storm loads the data into Cassandra, merges it with the existing data that's coming from our legacy system, and then we have the client deliverable. And in the last phase of this, we're going to turn off the relational JBoss system. And at this point, this is the current stage we're at in production. Now, one big help that, one tool that really helped us with this process was Oracle Advanced Queue. So you saw on the last slide I had triggers. So these triggers allow us to place messages on JMS queue and integrate our relational database with our real-time JMS system. Then, to actually seed this system, we place all the messages onto the queue. So we iterate over all the rows in Oracle, place those messages on the Oracle queue, and then consume them through a real-time system as if it was live data. One note on that is we found that the Oracle queue performs best if you keep only your working set on the queue at any given time. Now, if you have a distributed system, which we have Oracle RAC and then distributed consumers on the JMS side, then you have to think about how do you about concurrency and how this data is going to play when you have two transactions at the same time. So that gave us two approaches. We either place the entire row onto the JMS queue with the systime, and then we write to Cassandra using that systime, or we will write just the ID to the JMS and then query back to Oracle for the actual data. Both approaches work pretty well. There's cons to both. In the first approach, you have to make sure your clocks are very much aligned on your Oracle rack, or else one node will tend to win in the concurrency race over the other. On the row key, the only problem we ran into there is if you don't commit your transaction quick enough, the transaction could still be open when the JMS pulls the message off of the queue. So we ended up introducing a slight delay when consuming in that fashion. I wanted to talk about, after we have this system in place, how do we test this? So we use in-memory mock Cassandra. So we have found that Cassandra is very easily modeled in memory with map string, map string, map string, string, which is key space, column family, column, row key. And then the value is either string or object, depending on the complexity. We handle a lot of strings since our data is very unstructured. And then for our integration test, we have a superclass that starts up our Cassandra, migrates our schema, and then goes into the unit test itself. And after the unit test is done, come back to the superclass to clean up the Cassandra and bring it back down. Which leads me into how our quality assurance changed a little bit with this. So we write REST services for almost all of our services. This allows for SoapUI integration very easily. So we use SoapUI to test our software, and our QA team will develop the SoapUI test at the same time as our development team is developing the software. So we'll have our development cluster, and QA will go in there. They may find bugs there, and we'll fix both the SoapUI bugs and the software bugs. And then when that software is ready, it gets promoted to a test environment where we have Jenkins run the SoapUI through Maven, and we get automatic regression at that point. Now, as we've been using Cassandra, we found that the team structure was very important. We added development operations to our existing team. In the early days when we were first using Cassandra, we didn't have a dedicated DevOps resource. And we found this was a struggle. We added a DevOps person to manage our Puppet scripts, and this helped smooth things out quite a bit. And I want to talk briefly about our infrastructure and how we actually deploy our software. So we use VMware to deploy as our boxes. I know virtualization is very much frowned upon, but the main argument for why we use virtualization is so we can spin up a cluster at any point. So if finding a bug in production, we'll spin up a cluster to test that bug and then tear it down after we're done. To spin up these boxes, we use Puppet for all of our installs. So we run a single Puppet command, and that brings up a box for us. We have two ways of doing this. We use Puppet Master, place a message on the queue. That will then come in and install the box. Or you can use Jenkins, so push of the button, and then the box will come up to whatever version we need. And then that means that the same script that was run in development environment is then run in production. The only thing that changes is the host names and the config. So you may have a bigger box in production, so you would have some config tweaks. Now I wanted to switch gears a little bit here to talk about a real-time system and walk you through that architecture. So we start with that REST API that it talked about with Drop Wizard, and that goes onto a Kafka queue. So we put all the data into Kafka, and then Storm can rapidly pick up that data off the Kafka queue. It writes it down to Cassandra, and then we also write a copy of that data in JSON format to Elasticsearch. And then what Elasticsearch does for us is, out of the box, we get a Google-like experience for all of our data and all of our practitioners. And then we also have some custom things that we do with Elasticsearch as well. Now, why do we choose Storm? It's got guaranteed once delivery for all messages. And then it's also a very fast distributed system. So we write against the Java API all of our business logic and our data flow, and then Storm distributes that for us at a linear scale. And then it's also got a lot of momentum in the community right now. To integrate Storm and Cassandra, we created an open source project that's Storm Cassandra. This allows you to integrate their business logic from Storm and then write those values down to Cassandra, or vice versa. You can read data from Cassandra to kick off some of your Storm process. This integration piece is done through an interface with a mapper. So you'll implement one interface, and then that interface determines how you translate your business logic from Storm to Cassandra, and then back from Cassandra to Storm. I want to talk briefly about our vision for the future. We are currently experimenting with graph databases. We have Neo4j in POC, and we're looking at Titan to see if we can have a single persistence layer to help on the DevOps side instead of having another store. So we have right now Cassandra, Elasticsearch, and then we either go with Neo4j or Titan. We have very related data. So that's where that's looking. Last thing I wanted to say is just in summary. We have the Cassandra indexing project, which gives you alternate key. We have Oracle Advanced Queue, which helped with the integration between a relational database and a NoSQL. And then we have our Storm Cassandra project, which then gave us integration between Storm and Cassandra. With that, if there's any questions, yes? The speed. Kafka is very performant. It's pretty much the fastest queue out there that we found. It's consumer-based. So with Kafka, you put all the data into Kafka, and then the consumer keeps track of where it is in the queue. So if it's, you have the offset, which I can. So this offset here on the bottom left, the consumer keeps track of that inside a Zookeeper. So Zookeeper makes sure that two consumers don't have the same offset, and that increases performance quite a bit. Any other questions?
What version of Cassandra are you using?
So there's, I can tell you, in production we have 107, and in UAT we have 121. So, yeah. So
are you using the Thrift interface?
we used the Hector on top of Thrift, and we also use Astyonics on top of the Thrift. For real-time just querying, we use Virgil, which is a REST API.
So how long it took you to do this transition from SQL to non-SQL?
It's a process. Like I said, we're right now in the middle where we have both systems up. It was probably a year to get the initial piece, and then we've been in production for about a year. Yes?
Integration between Cassandra and Elasticsearch.
Yes.
Is it similar to the integration that Cassandra does, or is it directly writing from Storm into Elasticsearch?
Yeah, it's so right now Storm writes to both, so it'll drop the same data that is put in Cassandra. It'll drop into Elasticsearch. So Cassandra, we don't do anything directly from Cassandra to Elastic.
Last situation, have you faced any issues with, if a commit in Elasticsearch fails, that Stacker succeeds, how do you deal with data integrity in that situation? Does Storm offer you something to do that?
So Storm guarantees once processing, so it won't actually acknowledge the message as completed until all systems have said that they stored it.
Okay.
Yes. Inconsistent writes. We haven't. We do consistency level quorum, and we haven't faced issue like if we've had Cassandra certain nodes go unavailable, and then Storm will replay those if there's a failure, and it will just rewrite it. I'm not sure. Storm guarantees one success, so Storm will make sure that if there's a failure, that it gets retried. And then if it completely fails out, then you go to a dead letter queue. Which that's not, the dead letter queue is not part of Storm. It's something else. That's custom. Yeah, so the processing was a week before, and then now the current processing is a day for a record to go through. And then we're looking at 2 hours for the new system. Yes, here.
So is all your searching through Elasticsearch when you're doing lookups for your data?
We do direct lookups through the secondary index, or not secondary, the Cassandra indexing. For any fuzzy, we do Elasticsearch.
You guys keep them in sync forever, or is Elasticsearch
Yeah.
just a...
Elasticsearch is always current. Cassandra is over time. So we have all records for all time.
When it comes to sort of data retention, do you, like if it's a search index, just keep growing and growing and growing, or do you bring that very high?
It's only current data, so it's...
I guess what's current mean, I guess?
So current is we have 6 million active practitioners, but we keep track of them throughout the 10 years. So given any point in time, we can say what a practitioner looked like. So the data tends to, there's not a lot of new practitioners that enter in. So does that answer your question? I saw one in the back. I'm not sure how many questions do we have time for? I think we have time for. Yeah. Just the number of sources. So we generate a schema for every one of those sources, like to keep metadata, and it's just the manpower of you have to go through. We're migrating one source at a time. I guess last question.
Delve into why data. It seems like a week or a day or even 2 hours processing time seems long, just from a very generic standpoint. What was the cause of the problem, and how did, what part of the system Cassandra thought the Storm actually helped?
So in the old system, we would do data checks, and we would run through the entire universe and look for data that was inconsistent or didn't line up or got changed wrong. In the new system, we use Storm to run those data checks as the data changes. So that allows us to have much smaller pieces of data going through. And then trying to think what the other thing is the pure export and lookup time. We found the relational database was much slower for individual fetches. So Cassandra sped up the individual row fetches. We actually have a cache that's implemented in Cassandra where it pulls data from Oracle and then caches it in Cassandra to deliver records faster. And I think I'm out of time. All right. Well, thank you very much for coming.